This video is going to talk about standards of measurement, accuracy, precision, and significant figures. In science, we use the metric system. Below is showing you some of the base units that are used for measuring in science. So if you take a look at it, for length we use meters. For volume we use milliliters or cubic centimeters, which is centimeters with the little 3. And it actually looks like this. It's a superscript 3. For mass, we always measure mass in grams, and for density, we measure it in grams per milliliter. Temperature in science is typically measured in degrees Celsius. You'll also sometimes in this class see temperature in Fahrenheit or in Kelvin, so it's important for you to know the conversions from Celsius to Kelvin and to Fahrenheit. You can see those in the chart here, how those different measures of temperature relate to each other. In science, we measure time usually in seconds. Electric current we measure in amps, which is abbreviated with the big A. Light is going to be measured in candelas, which you really won't see much of in this class, but it's good to know. And the amount of substance, we use Avogadro's number, which we'll talk all about later in the year, and that's measured in what we call moles. Not to be confused with the little rodent moles. These moles are telling you about the number of particles in a substance. All right, let's look at some practicing measuring volume, mass, and length. Volume is measured using a graduated cylinder. Graduated cylinders are great for measuring the volume of liquids, but they can also be used for finding the volume of irregular objects. So for example, what you could do if you have an irregular object and you want to find the volume, you could use this graduated cylinder and fill it up with water up to the 5 milliliter point. Then you could drop in your irregular object. So let's say it's this big circle thing, drop it in there, and then you could measure how much that water rises. So maybe the water rises 5 milliliters up to the 10. So you know that since you started here at 5, and then after you dropped the irregular object in, it went up to 10, that the volume of that irregular object is 5 milliliters. So that's how much it made the water rise. So you can use that procedure for finding the volume of irregular objects using a graduated cylinder also. When you're measuring volume with a graduated cylinder, you should be able to measure the volume of liquids pretty precisely. The precision does depend on the size of graduated cylinder you use, but most of them are marked in 5 milliliter increments, and you should be able to look at the graduated cylinder and see where it is to the closest line, and then estimate between the lines too. And I'll show you an example of that. Now let's take a look at this 100 milliliter graduated cylinder. So you can see it's marked in 10 milliliter increments, and then it also has the 5s are these lines that are a little bit longer. So this one is like 95, this one is 85. And the marks in between those, these shorter marks, those are each 1 milliliter apart. We can tell that because it would go 80, 81, 82, 83, 84, 85. So using this graduated cylinder, you should be able to estimate your measurement to the tenths place. Remember, the tenths place is the one that's 1 digit after the decimal. It's important when you're looking at a graduated cylinder to figure out what each line represents. So on the 100 milliliter we looked at on the last slide, each line represented 1 milliliter. However, some of them are set up differently. So if you look at this one, that is 10 milliliters, right here, you can see that that one is actually marked for every tenth of a millimeter. Some of them are measured in 0.2 of a milliliter. So you just need to look and check how many lines there are, and then count the divisions between consecutive numbers. So if between 2 here and 3, there's 10 little marks, then you know that each one of those is 1/10 of a milliliter. So within the 1 milliliter span, there's 10 marks. When you look at a graduated cylinder that has a liquid in it, you're going to notice that the liquid kind of curves. We call this curve a meniscus. And it's important to know when you look at this where you're going to measure along that curve on the graduated cylinder. So basically you're going to measure at the horizontal center or the inside part of the meniscus, the bottom part right here. So wherever the bottom of that curve touches, that's where you measure. So if we were to measure the liquid in this graduated cylinder, we know it's at 5, and then we can count the little marks. We know these are 1 milliliter each because of the way they're divided out between the 5 and the 6. So it's 5.1, 2, 3, 4, 5, 6, 7, 8, 9. So it's 5.9 milliliters. That would be the correct measurement from this picture. Make sure when you're reading from a graduated cylinder that you move your eye to where it's level with the top of the liquid in the cylinder. And again, remember that you're reading from the bottom of the meniscus here. So take a look at this graduated cylinder and see if you can figure out how many milliliters are in it. And there's your answer. Now take a minute to look at these drawings of graduated cylinders and reading the measurements off of those. And you can check your answers, and if you have any questions, ask your teacher. Here's an example of how to find the volume of an irregular object in a graduated cylinder. So here you can look at this first cylinder, and it looks like it's at about 50.0. And then the second cylinder that has our irregular object dropped in it looks like it's at about 75.0. So to get the volume of the object, you would just take the one with the object dropped in, 75.0, and subtract from that what it was before it was dropped in, so 50.0. And your answer, in this case 25.0 milliliters, would be the volume of your object. Alright, like we talked about earlier, mass is going to be in grams. That's the SI unit used in science for mass. And there's a couple different kinds of balances that we use. So we use triple beam balances, which is what you see here. And then we also use some digital balances. It is important for you to be able to know how to read the triple beam balances. So if you look at this one in the picture, you always start with the largest. So on here we're in this line first, the one with the hundreds. So you know this is 300. Then you go to the next largest, so 370. And then you go to the next largest, which is 3. So you know it's 373. And then you also have to look at these little tick marks. So this is 3123.3. So total, this measurement is 373.3 grams. That's how you would read it off the triple beam balance. When we talk about accuracy and precision, you need to know the difference between those two words. A lot of times you'll hear them used interchangeably outside of science class, but in science class they actually mean two different things. So precise means that all your results are very close to each other, and they're usually very reproducible. So an example of one that is precise is like this one, the third one. So you've got 4 marks and they're all very close together. That would be precise. Okay, and then for an example of one that is accurate, accurate means it's actually close to the true value. So for this, the true value is the bullseye. That's what we're aiming for. So on number 4 here, those ones that are all real close to the bullseye, those would be accurate. And actually in this case, because they're close to the bullseye and also close together, we could say that it's precise as well. So remember, precise just means they're close together. Accurate means they're actually close to the true value that you were aiming for. So in science, we talked about using the metric system. So something with the metric system that you need to be able to do, which you've probably seen before, is you need to be able to convert from different units in the metric system. So metrics are pretty easy because they all follow the same pattern. They have prefixes that go along with multiplying factors. And each prefix has a symbol or abbreviation. You can see that in the middle. And a good way to remember these, I know a lot of people have seen this different ways with different acronyms, but my favorite is this bottom one. I think that's the one most people have heard. King Henry died by drinking chocolate milk. So that stands for K, kilo, H, hecto, deca, which is actually DA, the base unit, which is 1, deci, it's the D, centi is the C, and milli is the M. And if you write it out in that order, it's easy to convert from one to another. Here's another way to look at the same thing. This one actually has some more extreme ones like nano, mega, and giga. You won't really see those as much. We'll basically stay here. But you can see again, we've got kilo, hecto, deca, the base, deci, centi, and milli. King Henry died by drinking chocolate milk. So that's a good way for you to remember it. Alright, let's look at an example to review how you convert from centimeters to kilometers. So this is just one conversion you could do within the metric system. So I like to do what I call the bump method, which you've probably seen before. So it says that we've got 20 centimeters. We want to know how many kilometers that is. So I'm going to start here because my decimal point is by the C for centimeters, because your decimal point would be here after the 20. So I'm going to start here, and then I'm just going to go bumps until I get to the K, which is what I want for kilometers. So 1, 2, 3, 4, 5 bumps. We stop right after it where the decimal point would be. And then however many bumps you did up here, you're going to do that same number of bumps on your number here. So if we had 20, then we'd take the decimal point and go 1, 2, 3, 4, 5 bumps. So your decimal point is here now. And these extra bumps that don't have anything in there, you're just going to fill those in with zeros. So your answer here would be 20 centimeters is equal to 0.0002 kilometers. Alright, let's try another example. This time we're going from meters to centimeters. So meters is the base unit, so we'll start here. We're going to centimeters over here. So we do 1, 2 bumps. So on the 10, we've also got to do 1, 2 bumps. So your decimal point's now there. Fill in with zeros. So your answer here would be 1,000 centimeters. Alright, another thing that you need to go ahead and put in your notes is the formula for density. I know we've seen this before, but just a reminder, density is equal to mass, which is always in grams, divided by volume, which is always in milliliters. And if you have a hard time remembering that formula, kind of a cutesy way to remember it, so you can draw a little heart with a line through it, and you can kind of see the mass divided by the volume. That's your formula for density, so that can help you remember it. Another formula you need to know is the percent error formula. So here it is right here. Make sure you get that formula down in your notes. And when we're talking about the theoretical value, that's the actual value, the known value, or the true value. If you see any of those words, you know that's the theoretical value. And the experimental value here is the one that you find in your experiment. So just as an example of how you would set this up, if you were trying to find the percent error in a situation where the actual value was 4 and the experimental value was 5, you would plug it in like this. So your actual value, remember, is your theoretical, so that's 4. Minus, and then I put in my experimental, which was 5, divided by, I'm just following this equation, the theoretical value, which is still 4, and then I need to times that all by 100. So you would just plug into the calculator 4 minus 5, which will give you -1. You do -1 divided by 4, and then times that by 100. And that should give you, if you put it in your calculator, -25. So your percent error is -25%. But these little lines here and here, those stand for the absolute value. So absolute value basically means that you don't put the negative sign. So even if it's a negative, you just leave that part off. Absolute value means you just change it into a positive. So your actual answer that you'd say is 25% error. One of the things that may be new to you is significant figures, which we call Sig Figs sometimes for short. So there's a lot of rules that go along with significant figures, and basically the rules tell you which ones count as being significant and which ones don't count. So here's the rules, and you do need to know these. So the first rule says all non-zero numbers are significant. So if the number is not 0, it's definitely significant. So that's an easy one. The last 3 are about zeros. So the second one says zeros that are located between non-zero digits are significant. We call those sandwiched zeros because they're in between two numbers that aren't zeros. So you can see some examples of those there. All of those zeros would be significant. They would count. Trailing zeros are zeros that are at the end. So they're after a non-zero number, and those are significant only if the number contains a decimal point. Otherwise, they don't count. So you can see in the examples, this first one has a decimal point, so that 0 does count. Second one has a decimal point, so all those zeros count. Third one, no decimal point, so none of those zeros count. The only ones that would count are the two non-zero numbers, the 1 and the 2. And the last one says zeros to the left of the first non-zero number are insignificant. So we call those leading zeros, and those zeros never count. They're just placeholders. So in all 3 of those, none of the zeros count because they're all leading zeros. Alright, if you're still confused about significant figures and when zeros are significant and when they're not, here's a little trick that can help you out. So we got a map of the United States, and we know over here, this is the Atlantic Ocean, so we're going to put A for Atlantic. Over here on this side, this is the Pacific Ocean, so we're going to put P for Pacific. So here's how the trick works. P is now standing for present. So this is saying there's a decimal point present. So if there's decimal point present, you're going to start counting the zeros going this way after the first non-zero number. So if I have a number like this, I start counting, okay, we're still at 0, still at 0. Oh, we got a non-zero number here. So I know everything after that non-zero number is going to be significant. So this one would have 3 significant figures. Alright, from the Atlantic side, this is if the decimal point is absent. So if the decimal point is absent, you're going to start counting going this way from the first non-zero number. So if we look at 120 with no decimal point, going this way, we're still at 0, and then we get to a non-zero. So we know we're going to count only the things that are past that non-zero number. So this one would have 2 significant figures. So try that out when you're doing your Sig Fig problems, and that trick helps you, then great. If it doesn't help you, then you can just go back to rules 3 and 4 on the previous slide. Okay, the last of the rules for significant figures have to do with when you're doing math with significant figures. So the first rule's about addition and subtraction, is that your calculated value can't be more precise than the least precise quantity used in the calculation. So the least precise quantity is going to have the fewest digits after the decimal point. So your calculated value that you get when you do addition or subtraction has to have the same number of digits after the decimal point, to the right of the decimal point. So if you take a look at this example here, if you're adding these numbers, the one that has the least number of digits after the decimal point would be this one, and it only has 1. So when your calculator spits out this answer, you're going to round that to only having 1 digit after the decimal point. So it's going to be 25.3. That would be the right answer according to the rules of significant figures. And you do the same thing for subtraction problems. Okay, and then there's a different rule for multiplication and division. So for multiplication and division, the number of significant figures in the final calculated value will be the same as that of the quantity with the fewest number of significant figures. So now you're not really worried about where the decimal is, you're just worried about how many significant digits it has. So if you look at this example, you've got this 27.2 has 3 significant digits. And then the 15.63 has 4 significant digits, and then the 1.846 has 5 significant digits. So you're going to use the one that has the least amount of significant digits, so that would be this one. It has 3. So when your calculator gives you this number, you're going to round that to 3 significant digits. So it would round out to 230. And the last rule is just talking about if you have addition, subtraction, and multiplication, division. And what you would do is apply your rules for addition, subtraction first, and then go ahead and do the multiplication and division rules after that.